All right, then I will introduce our speaker. Tomas is a sixth-year PhD student at UCSF in the integrated program of quantitative biology, um, which is a big umbrella program. But I think he's technically in the bioinformatics program. So he's a computational biologist by training, and he's in Orion Weiner's lab, and he studies cell size control, especially of neutrophils, if I remember correctly.
That's correct.
And uses Julia in everything that he does. And actually, when I joined the program, I'm a UCSF student as well. When I was a first year, I remember being so impressed with Tomas and Julia that I got really into Julia as well. So much so that I bought a sticker and put it on my computer. So if that's you after today, you're in good company. Yeah, hopefully this is a really informative seminar, and you all are inspired to learn a new language and I don't know, get started with Julia. So without further ado, I'll let Tomas take it over. And like I said, if you have any questions, put them in the chat, or it sounds like Tomas is comfortable with being interrupted with questions. So whatever you feel more comfortable with.
Awesome. Yeah, thanks, Matt, for those words, and also for the organizers for letting me come talk to you all. And also, yeah, actually, I think it was Krista, one of Matt's what do we call them, like program mates, who got me my Julia sticker too. So so I owe them for a Julia sticker as well. But yeah, I'll go ahead and get started. All right, can people see my screen? Okay, awesome. Yeah, so the title of this talk is leveraging Julia for data science. And as Matt introduced me, I'm Tomas. I'll just a brief background on my history in Julia. I went into my my GitHub history and found that my first kind of commit using Julia was I think in 2014, about 6 years ago now. I was like, oh, cool, new language. But then I think I started using it full time about 4 years ago, and as Matt said, I use it for almost everything that I do in my work. But yeah, again, as Matt and others mentioned, please feel free to interrupt me with questions as I go. This is an interactive experience, I hope, and I'll try to keep us on time as well. So before I get started, I think this is a very large and complex topic. There's a lot of aspects to data science, and I won't be able to cover, I'll just be able to cover just a very small part of it. There are fantastic guides already out on the internet that that are going to do a better job than I can in an hour. One of my favorites is from UC Irvine. Their data science initiative has a great guide that has like a bunch of well-commented Jupyter notebooks that I think are fantastic. And they do a great job of introducing Julia and explaining the nuances of the language. How do you get the best performance? How really like it runs the gamut, everything from deep learning to image analysis to statistics and so on. So I highly recommend this resource, and I'll bring it up again at the end. But you know, again, I don't want this talk to be really a tool-focused talk, because I think, again, I can't do those tools justice in this time. That said, there are a bunch of fantastic tools in Julia. I think I just put the names out here of many of them, just so that you all can go and find them later and, you know, see and Google them, and they have great documentation and so on. So just to start off, you know, like there's a great data frames package called Dataframes.jl. So that would be similar to pandas in Python, or R's built-in functionality. There's also like a great querying like to work with the relational data to query relational data. It's called query.jl. There's also lots of packages for loading your data into Julia from CSVs or SQL databases or whatever. There's also great plotting libraries. There's Gadfly, Plots, pyplot.jl. Pyplot.jl is pretty cool. It's just a wrapper around matplotlib. Julia can interface with Python directly, and it can use Python objects directly. NumPy objects can be passed back and forth in memory, which is fantastic, like sharing the same memory. So it's actually, you can just use matplotlib, so you don't even have to learn a new plotting library. Though I'm partial to, as a maintainer of Gadfly.jl, which is a grammar of graphics style library, so like ggplot in R. There's also IDEs like iJulia, Jupyter Notebooks. The Ju in Jupyter stands for Julia. I'll actually be using a Jupyter Notebook here in a second. There's also Visual Studio Code. Has like nice support for Julia now. There's also statistical packages. I think these are quite good. Distributions.jl, hypothesis-test.jl, so on. Also, the deep learning ecosystem, I think, in Julia is excellent because I think Julia is extremely well suited for deep learning. I think the basically tour de force library is flux.jl, but there's also, you can access TensorFlow through Julia. Personally, my money's on Flux to eat the world, but that might be a ways out still. But there's also a great image analysis ecosystem. I use this one extensively, called images.jl. This is sort of similar to scikit-image in Python, but I think it has like the best scientific image processing suite of any language. And it's incredible how powerful it is and how fast and robust. That is where the real advantages come from. But again, this is not a tool-focused talk. I think, I would really want to talk about like why you should use Julia for data science in the first place, given that there are many other data science ecosystems out there. And what does Julia bring to the table that those languages don't have? And I think it really boils down to the fact that you can have the speed of C and Fortran, but with the rapid development and readability of Python, R, and MATLAB. And this, I want to break this down for you for a second. Like, why is this important? In a lot of, currently in a lot of these languages, like Python and R, you have that nice high-level language benefits. Like you have the interactive, rapid development where you can use Jupyter Notebooks or RStudio or whatever. Quickly generate plots, quickly develop your code, debug it in real time. Like the tooling is really nice. Packages are really nice. But the problem is that usually for prototyping, it's pretty good. But the moment you actually want to transition it to being fast, being general, and like releasing a package that other people can use on data sets that might be much larger than yours, you have to rewrite a lot of the code in C or Fortran to make it fast enough to use in a general case. And that's a huge barrier to entry. Packages that involve two languages are much harder to maintain. You have, it's much harder for new people to join the project and learn, because as a user of these languages, of Python or R, you have a lot of skills. You acquire a lot of skills in how to use the language. But then those skills aren't useful to develop a language, because you're probably doing that in something like C, which is drastically different. And then vice versa as well. As you're a developer, you don't benefit as a user. And so how does Julia get around this? Like what, why can't you get around this just by making Python or R faster? And a lot of people like to, I see this commentary on the internet that like the only reason Julia is fast is because of its JIT, it's just-in-time compiled, and that you can achieve similar performance if you JIT Python, for example. Like there are projects such as Numba that do a fantastic job speeding up Python. But I think that misses the forest for like a tree, where the real advantage for Julia comes from the fact that not that you can get these other languages to be as fast as Julia in a limited case. It's that Julia is generally fast. Like it's going to be fast on whatever naive first implementation you do. is most likely going to be very fast. And if it's not, it fails for very reproducible, reliable reasons that if you know to look for those reasons and you can check, like it has great tools for checking if there are any problems, you can figure out why it might be slower than you expect. And so I'm going to talk about those in a little bit. So the real benefits from Julia that Julia has actually come from core design decisions that were made when the language was created. And this decision was essentially that they decided to have a language that has type inference and specialization through multiple dispatch. So what do I mean by that? That's sounds like CS gobbledygook. What type inference means is that whenever you have a type, if you set a equal to 3, Julia knows that a is now an int 64-bit integer, because I ran this on a 64-bit machine. And what this means is that you didn't have to set a to be an int 64. Julia inferred this based on the fact that you set it to 3, which is an int 64. It knows that. And similarly, like it can do a lot of these calculations to figure out, like as you write your code, what the final type should be by passing and doing, like following your code and following how the types are changing to figure out what the final type is. The other benefit is this other key aspect of Julia's specialization, where Julia always runs the function that is the most specialized for a given code. So in this case, I'm doing, taking a, which is 3, and adding 3 to it. And we can use this macro called which tells you which function is going to be called. And so in this case, when I print this out, I get the plus operator. The plus function operates on x and y of a subtype of that are of type T. This double colon thing tells you that it's of a type, where T is a union of all this stuff, right? But what is this stuff? If we look at it, it seems like a bunch of ints with some bit number after it and uints, so unsigned integers. So it looks like basically if T is a subtype of integer, we call this function where it's located in base Julia at int.jl. And so Julia knows that given that you have 2 integers as an input, it knows to pick the plus operator or the plus function that operates on 2 bit types, and it picks the most specific function that applies. And so the other thing is that if you look at how many plus functions there are, if you get all the methods, so this function called methods lists all the methods in the method table that Julia has for the plus operator. And what you can see is there's 184 functions in base Julia for adding. And what's cool about this is that, it doesn't really matter what all these guys are, just that, say, you all can see my pointer, right? Not completely sure if I can.
Yes, we can.
Okay, awesome. And so with the plus operator, for example, here we have like a float 16 added to a float 16. It knows to call that most specific function that operates on that. And so that's the specialization benefit. The other aspect of this is multiple dispatch, where what that means is like most languages, like common languages, use single dispatch. Like in Python, if you write your own function, the first parameter for every function is self. That means you associate a function with an object, right? Julia doesn't associate functions with objects. It operates on objects. What that means is that Julia dispatches, what I mean by that is it selects the function that applies, that where all the types of all the parameters match the function signature. And so if you provide plus with 2 float 16s, it knows to go and find the plus that takes 2 float 16s. What this means is that you have a language where you can add your own methods to this method table. You don't need to, like in Python, it's actually like, it can be difficult to add your own function to an object that was already created. Like you have to inject the function or whatever. In Julia, you just have to just define a new function and it will be added to the method table. And if it's the most specialized function that's available, Julia will use it wherever that function is used. Which means that you have a very extensible like language where you can define your own functions and they will be used wherever that function is used. And so these core design decisions, again, I think it will help once I show you all. I'll have an example where I'll actually use these. But these core design decisions are where the advantages that you might have heard about come from. So one of the main ones is speed. Given that you have types, type inference, and you can specialize and figure out which function is the most specific one, and that those can be hyper optimized, you can end up with extreme speed. So you can have the speed of C or Fortran, but with the maintainability and readability and development of a high-level language. And so you can actually write code that is faster than C or Fortran because it's easy to write algorithms that might just be too hard to maintain in C or Fortran. Just because they're too complicated, it ends up being too big of a maintenance cost. While in Julia, you have all those high-level abstractions still available to you. The other thing that you have is composability. You can combine functions in new ways where they don't have to know about each other. And given the fact that as long as the functions operate like you write them in a general way, Julia can, despite using type inference, figure out what should be happening, and you can get a lot of the speed benefits while still be super general with your code. Like a lot of times you never have to mention types anywhere, yet the speed is as fast as if you did. Another nice thing is extensibility. Is because of multiple dispatch, you can have functions and write your own functions, and it will, like base Julia can call your functions instead of whatever its functions are. And so you can really extend the language in new ways. And that's hugely useful. And there's no two-language problem. Like all these things come together, meaning there's no two-language problem. So even base Julia is written in Julia. Like if you know how to use Julia, you can read the Julia code base. 95% of the stuff in there is written in Julia. That's a rough estimate. And everything that isn't, like they're working on rewriting in Julia. And so like you can look at the full stack. There's nothing special about Julia code that's in base. So unlike some languages where, because they're actually written in C or Fortran, so in case of NumPy, you're like there's huge performance benefits using NumPy if you can rewrite your functions to use NumPy instead of Python, because then it's actually doing all the operations in C. But in Julia, there's no, you can write it however you want, like the naive way, and it's probably fast enough. Like you don't need to vectorize your code often. You don't need to, don't need to use the built-in functions if you don't want to. You can write your own. There's not, in general, there's not a performance penalty for that, which is fantastic. But I think the real advantage and what I want to focus on today is that for data science, like why you should use the Julia ecosystem for data science, is that, I kind of hinted at this earlier, but in most languages, the intersection, the Venn diagram of package users and package developers is extremely small, like the overlap. Because packages, again, are written in a different language, like even languages like Python are different. They have their own nuances. A lot of what a lot of your knowledge doesn't transfer. And so there's a large barrier to entry. And I think the real advantage of Julia is that as a user of the language, your day-to-day usage of the language makes you a better developer of the language, and makes your ability to transfer from one to the other much quicker. And so I think this is where the key of the language lies. And to kind of give you all a feel for that, what I'm going to do, show you all a case study here where I'm going to add a new feature to a base Julia library during this video call. This library is Statistics.jl, and I'll highlight Julia's advantages in the process. So we're going to see multiple dispatch in action, extensibility in action, the no two language problem also in action. And just really quickly before I do that, I'm going to introduce like a very small snippet of the data that I use in my work. And so what does this data look like? I take a lot of movies of single cells moving around, and I measure their cell size. And I can plot the cell size over time. So x-axis is time here, and then cell size or volume here on the y-axis here, normalized to time point 1. And the whole stack of image analysis and tracking and everything is Julia, except for I actually call a Python package that does a really good way, nice job of tracking cells. And I can track their cell size changes over time. And then I'm analyzing these traces currently. And so this full, like the whole image analysis stack is written in Julia. And so I want to focus for a second. I'm going to switch my screen here away from the slides to a Jupyter notebook that I have open here. And I guess I'll pause for a second if there are any questions at the moment.
There's just one question that's coming through the chat.
Yeah.
It refers to the 2 colons. I think it's the 4 dots someone's asking about. So when we're looking at the addition operator, you printed out the types that the addition operator works on, and there were colons in there. Maybe you can just explain really quickly again how exactly you parse that.
So these right here, these 2 colons here?
Yeah, I believe that's the question.
Yeah, so sorry if I didn't make that clear. Essentially what that means is that what that says is that as the definition of, maybe what we can do is actually, let me do this because this shows off a nice feature. So if we do, so let me actually start. So I'm just gonna, I'll answer that question in just a second. I think I know how to do that. But before we get there, I'm just going to quickly show some simple code here, where if you set a equal to 10, Julia knows that this is kind of what I was showing in that slide. Julia knows that a is an int64 because 10 is an int64. And so Julia knows that if I add an int64 to an int64, I can ask which function is actually combined here. And so again, it shows this x with the 2 colons and then a t, where t is a union of all these variables. What you can see is there's a nice little hyperlink that comes up if you're in a Jupyter notebook, and you can click on it. And that actually takes you to where in the base Julia code. So this goes to GitHub, Julia Lang/Julia. And it actually highlights where that function lives, right? So here's the plus function. It takes an x of type t and a y of type t. So the double colon here says that x and y have to be of the same type. Where the t must be a subtype of bit integer. So this where here says that t is not defined, and so here we define t to be a subtype of bit integer. And so it knows that if you're trying to add 2 bit integers, you can specify that with the double colon here, and then it will call addInt function, which is lives somewhere else in base. And so this way, there are other plus. Here's another different, or I guess that's a asterisk. So that's a multiplication operator. Does that answer the question? Sorry, I'm not sure. But maybe I'll keep going, and then if there are any more questions on that, I can try and answer those. So again, that's just sort of like you're specifying the type of x and y. So that's the case where we added 2 integers, right? So what if we do, so 10.0 here is a float, right? So if I ask what the type of 10.0 is, Julia knows that that's a float 64, right? So it's a floating point, 64-bit floating point number. And so if I do which, I do the which command where I add an integer to a float, now what we see is x is a number, okay? So again, there's the double colon, which means that the type is number. And as you can tell, that's a lot less specific sounding than this here, where that was a bit integer. So that means Julia always picks the most specific function, right? And so in this case, you know, an int plus a float, well, it goes up the tree of all, like the tree of types, and finds that the first time there's an intersection is when they're both numbers. And so, you know, here it's linking to promotion.jl, which suggests that it will promote the types to find a uniform type that matches. So if we actually run this, so if we do a plus 10.0 and we ask what the type of this is, what do you all think it is? It's going to be float, right? Because it finds a uniform, like it tries to promote the types to a uniform type, which in the case of an integer, it's easier to promote an integer to a float than it is in the other direction, right? And so like if you have, you can also convert a float to an int, but there you have some issues. Like if you try to convert a 10.5 to an integer, you get an inexact error because now it knows that there's no way to represent that number as an integer. And now if we actually consider the third case where we add two floats to each other, again, now it's finding the plus operator that is specific to float 64. So it knows how to add two float 64s. And then it's calling a different plus than integer. And you can see that's even located in float.jl instead of int.jl. Okay?
There's one more
and
question
so,
that came in related to this.
Yeah.
It's which one stands for X and which one stands for Y? And I'm unsure. Lee, could you clarify the question? I want to make sure that we answer this. I don't think I fully understand what the question is.
So I think he might be asking this. So this having this plus in here is just syntactic sugar, is what it's called. What this actually mean, what's actually happening is this: the plus function is called in this way, where to say, let's do 5.0 here, so you can actually tell the difference. So if you add 5.0 and 10.0, that actually gets remapped into this. So that gives you the same result. So it's calling the plus function, and since it's multiple dispatch, right, the plus function doesn't belong to anyone. So it's not like you know, in some other language, oh shoot, in some other languages you might do, you know, something equivalent to, you know, the plus function belongs to 5.0, and then you do plus 10, right? In Julia, the plus function operates on types. And so you have 5.0 and you add it to 10.0. And so the x here is 5.0. So that's how it maps. And then y is 10.0. Does that help?
Yeah, kind of. Thank you. I think in the previous example, just to show a single number, but still have X and Y. So that's why I feel confused.
Okay.
I think in your slide somewhere, you just type at which or something.
Yeah,
oh,
at which.
Actually two. Sorry.
Yeah, it's a plus 3, yeah.
Oh, okay, I see. It makes sense then. Okay.
Okay.
Thank
Cool.
you.
Thank you. All right. Yeah, and feel free to interrupt if anything's not clear. That's great to add some clarity. So now, in my case, so I work with these cell size, right? Well, I work with units, and it's important that my units are correct. So I do a lot of my measurements, and I put a lot of effort into actually getting units attached to my data. And this has a lot of advantages. I'll talk about this in a second. But there's this great package called Unitful. And in Julia, to import a package, so in Python, it's import. In Julia, it's using. So you can say using Unitful. And then I'm importing a couple like symbols from Unitful. And the way that you get these is that you can type \mu for mu. And then if I hit tab now, it converts that to the Unicode representation. And so that's how I got the micron here with the mu. So if we import Unitful, what this now lets us do is associate a unit with with whatever number you want. And so in this case, I'm going to have a type called B, where I'm going to associate a unit with the type. And so now it's no longer is it 5, like a dimensionless quantity, it's now 5 microns, okay? And so this has some nice benefits where I can try to add 10 to that, and now I get an error, which is correct, right? Like 5 microns plus 10, those aren't dimensionally compatible, and that's exactly what the error says here. Julia basically doesn't know how to add these two types. And so what we can throw a which on here. I haven't tried this and see which one it types. It tries to promote them to the same representation, but it can't, because there's no way to figure out, there's no way to promote 5 or like 10 to be a 5 micron. Like it can't convert those to the same type. And so that's where that error comes from. But what's cool is that if we then add a type to whatever we're modifying, so here I can divide by 2.5 microns and it knows that's 2.0. And now this is a dimensionless quantity. So if I throw the type of this, you just get a float 64 back. So it knows to cancel out the types. Well, how does it, well, I'll get to how does it know in a second. But now say we do something fancy and we want to know like how fast is a cell moving per second or something. So we can divide by the unit in time. And what you get now is it says if 5 microns divided by 5 seconds gives you 1.0 microns over seconds, right? And the way that Julia knows this is that if you look at the type of B, this is going to look scary. It's a quantity where, so quantity is something that Unitful introduced. So we can ask what quantity is. So this little question mark will print the documentation for you. And so what does that tell? It like prints out what quantity is, and it's a subtype of quantity, abstract quantity, and it's it has a type parameter T, D, and U. So that's the TDU here. And so the T is, that's the numeric backing type. So what's the actual, how is the number represented? So in this case, it's an N64 inside of it. The D is dimension. So in this case, it's L, which means length. It's a unit of length. And then U is like what the actual unit type is. And so in this case, it's microns here. And so if we look at the type of like 5S, so in this case 5S, what you can see is again N64 is the backing type, but now the dimension is type T. So it knows that seconds have a different dimension than time or than length, and so you can do interactions with them. And the other thing I would like to point out here really quick is and then we can do like a quick sanity check. For example, for all my cell size measurements, I use volume, which is cubic microns. And so just to check, like 1 femtoliter is equal to 1 cubic micron, and it knows that to be true, which is great. And the other nice benefit, oh yeah, this is what I wanted to show, is that if you actually dump the type, so dump lets you look at the raw representation of a type. What you can see is that all this is a fancy wrapper. So this is the type. It's a fancy wrapper around an integer, which means that this is really fast, which means that you can generate tens of millions or whatever of these units, and there's no performance penalty for doing that. Like we could do, you'll see here in a second, like we'll be generating 100,000 of these numbers, and it's basically instantaneous because it's almost as fast as just working with integers. But now we have a very useful associated information. So we can associate different things with the types. So there's another useful package called measurements where you can associate an error with each type. I can show that if we have time at the end. But in this case, we're associating units. And so we can also, I'm going to generate some random data really quick just to simulate my data. So we can, use rand. Rand function is very similar to most other languages, where we can get create a little array or vector in this case. Again, the type here is quite specific. It says that this is an array of float 64, and this little 1 here says that it's has 1 dimension, so it's a vector. So if we generated, I don't actually know if this is going to work. Oh, cool, good. Now we have a float 64, but now there's a dimension of 2. So this is now a matrix instead of a vector. But we can go back to again, there's a lot of information encoded in the type. Where in other languages, you would have to query the type and be like, oh, like what's your size, like what's your dimension, so on. That's actually stored in the type for Julia, which means that Julia can actually dispatch on that, which means that if you write a function for vectors or a function for matrices, you can just specify 2 or 1 in the function type signature, and it will know which one to pick, and it can operate on those and pick the most specific one, which is great. Another fun little feature is that if we make a vector here, 1, 2, and 3, and we want to add 3 to it, what you'll see is that we get an error because Julia doesn't have a concept of adding an integer to an array. But this very helpful error says, for element-wise addition, which is what we were trying to achieve, use broadcasting with the dot syntax. So array dot plus scalar. So in this case, if I just go up here and add a dot, it will now add 3 to every single element of the array. And this is specific. So like like if you do multiplication, again, it will try to do matrix multiplication unless you specify element-wise with the dot. Which this is important. This is very consistent across all Julia functions. Makes it very easy to know if you're doing element-wise or not, which a lot of languages don't have that clarity. And so in this case, I'm going to generate 100,000 random numbers from a uniform distribution. I'm going to multiply them by 20 and add 490. Doesn't really matter. Again, I'm doing element-wise multiplication, element-wise addition. And then I do a multiplication with cubic microns. The reason I'm doing this is about 500 femtoliters is about the average size of a cell that I measure. So we can generate that. And so now we have 100,000 volumes. And here again, the array is 100,000 elements long, and Julia knows that it's full of unit-full numbers, like it has units on there that are backed by float 64. The dimension is length cubed, which is exactly what we expect, and it's microns cubed. And this is great because yeah, this is quick to do. And now what we're going to do is, like, I was doing my work and I wanted to compute some basic statistics on these numbers. So I import the statistics library, Julia's statistics library. This is part of base Julia. It's part of the standard library. It ships with Julia, so you can always just add using statistics. It's not imported by default, just to not contaminate the namespace. But we can import statistics. We need, like, mean. The function lives in statistics, so we can look at what methods are available for mean. What you can see is that, oh, it looks like mean can be run on a couple different things. All of these live in statistics.jl. And it looks like, you can compute the mean on, like, an abstract array, for example. Well, we have an array, right? And that's a subtype of abstract array. So we can just compute the mean of volumes, right? So I can run it again. So we can compute the mean of the 100,000 elements in whatever that is, barely any time. And we only did a single allocation to do that. So this is insanely fast. So there's basically no performance penalty for having all those units attached. That's super cool. We can also, the other really cool thing about this is might not be obvious at the beginning, is that statistics has no concept of units. So statistics has never, .jl has no concept of unitful.jl. It doesn't know what a cubic micron is, doesn't know any of that. It doesn't need to, because it's written in a general way. Mean can operate as long as the stuff that's contained inside of the array that you pass to mean, as long as that has a couple, like, standard properties. Like, if the stuff inside behaves like a number, you can compute a mean on it, right? And so even though mean has no concept of units, it can still compute. It still works. This is where the real power of Julia comes from. Is you can have packages that extend both the built-in libraries, or you can write stuff to extend packages and they don't actually need to know anything about your types to do that. So again, like standard deviation just works. Now let's try median. So this was actually came up in my work where, I tried a couple of different things like mean.
Moss?
Yeah.
If you did variance, would it have, would the units change?
Variance. I'm sorry, I don't follow.
Because it would be squared.
Okay. Yep.
Oh, okay, cool.
See, a lot of this stuff should just work. And so the same thing. Yeah, I mean, I've never used that function before, but yeah. That's a good question. And so, or maybe I'll just leave that there so we don't delete it. And so, in my case, I wanted to, like, I didn't know what it turned out my distribution was a little skewed, so I wanted to try median on volumes. And then we get a nasty error. Uh-oh, that's not good. So we get this error says no method matching middle of quantity and quantity. So again, we're trying to compute. It seems like middle is some function that gets called on two different types, and it seems like it tried to call it on our unit full types, and it doesn't exist. So this method doesn't exist, and you can see that it was called inside of median. So when we called median, it did some stuff, and then it called middle, and then middle doesn't exist for unit full types. That's not good. But wait, Tomas, didn't you just say that statistics.jl shouldn't have to know about unit full? Well, that's true. So there must be something weird going on here. So we can just print out methods of middle, and you can see that middle lives in statistics.jl. And it seems like this is the middle that's being called, or this is the only middle that has two parameters, X and Y. They're both requiring the types to be real. Okay, that's interesting. So it seems like maybe unitful numbers aren't subtypes of real. That's weird. So let's just we can ask for the first element of volumes. So in Julia's by default 1 based indexed. So if you get this gives you the first element of an array. And so if we get the type of that, and if we ask this question and we store that in unit type, and if we ask if unit type is a subtype of real, this little operator here tells you whether or not a unit, like it basically does the check if something's a subtype. But it turns out a unit full number is not a subtype of real, but we just, but like the number inside of it is a subtype of real, right? So this is oh yeah, you have to do it on the type, not the raw. So I have to say type of. Like that's true, right? So this means that unitful, the wrapper, like we wrapped our float 64s inside of unitful. Now unitful is not a subtype of real, and then statistics.jl got confused. So what's the type hierarchy here? So what we can do is we can get the supertype of the unitful quantity, and that is abstract quantity. Okay. What's the supertype of that? It's number. Okay. Well, real is a subtype of number, right? So that means that in the hierarchy, so I just stole this hierarchy map from Wikipedia for Julia. And what you can see is that real, so middle, the function, expects subtypes of real, while it looks like unitful actually lives above, like at the same level as real. And so if we get the subtypes of number here, so we can ask subtypes, it looks like, complex, real, and then abstract quantity. So it looks like units, you can have, it's probably why this decision was made is because you can have units attached to complex numbers as well. And so what we have to do now is that let's go and look at this middle. So, it's defined in statistics.jl. So let's just go to Google, type in statistics.jl, open it up in, open up the the file. So it says here it's in statistics.jl, source statistics, line 746. So let's check that out. So we're going to go into statistics.jl, and we said line 746. Cool. So that's exactly where I wish the hot linking worked. It doesn't work with standard library, unfortunately, yet. But here's the function that gets called. So you have middle, where x is a subtype of real, y is subtype of real. Well, there's no reason that shouldn't work for numbers as well. So we can just copy paste this into here, and I've already have it here. And what you do is you just take that, copy paste that function. We're gonna add number. We're just gonna change it number here so that we're gonna add support for number. And like this function here, like unitfuls support division and addition, so it should just work, right? You know, I have to add statistics middle here because it's telling me that it must be explicitly imported so that you don't accidentally overwrite a built-in function. So now that we explicitly say it, now I just define the function, okay? And now if we print out all the methods available for middle, what you can see is there's now 7 methods instead of 6. And the last little function down here is x and y are numbers. And now, and it tells you where it lives. It lives in this Jupyter notebook in cell number 48, line 1. Okay, cool. So now that I wrote a middle that works, Julia is going to pick the most specialized function that it has access to. And since we wrote the function, it's now in the list of all functions. So that means that median should use it. And it works. So that means that, so what's cool about this is that statistics.jl is using your function that we just wrote in your code base. Even though we didn't have to inject it, we didn't have to do anything. Because we wrote it and it added it to the method collection, Julia will just find whichever one's the most specific one. And since yours is the one that we just wrote is a very general one, it will try to find the one that's most specific. And if it can't, it's going to use yours. And so in this case, we did achieve, we got median to work. Cool. So now, you know, you could go happily along your way, but that's not how we do things. I think we should do some more fun stuff, which is we can actually fix this in the code base. And so I already git cloned this statistics.jl library. So I have it living on my computer here. And what I can do is, yeah, I can just show you all. So I have the statistics.jl folder. I just downloaded it. And what I'm going to do is you can check, like, this is the latest version. So I'm doing a little fancy version control stuff here. If you don't know version control, I highly recommend learning that. It's pretty useful. But what I want to show you all here is not any version control stuff. I'm going to fire up Julia to use the local virtual environment. It's not strictly necessary, but it's going to be useful in this case. So I'm going to import a package called Revise, which is fantastic. It lets you hot reload code that you have open in your REPL or anywhere you're using Julia. So if it changes on disk, Revise detects the changes on disk and loads in the new version. That's going to be very nice here in a second. And so I'm just going to add this long line. All it does is it sets us up basically where we were. So volumes is the same as what we had before, right? So what I'm going to do now is, you know, show you all that look, volumes doesn't work, or computing the median doesn't work, and it gives us the same error, this middle function. And so what we can do is go to Visual Studio Code. I actually have statistics.jl opened up on this line already. This is line 746, like on the GitHub page that we checked out. What we're going to do is quickly change the reals to numbers, like we did in the Jupyter Notebook, and we're going to update the documentations because we're good citizens. And then so that we fix that middle. There's actually, just to make this a proper pull request, we are also going to update the case where middle takes a single number. And so, you know, update the documentation here as well. And so I saved that, okay? So I just changed statistics.jl on my computer. And what I can do is now try to run median volumes again. And what you should, it takes a second because revise is detecting the changes on disk, recompiling everything, and then magic, it works. And so we just changed statistics.jl on disk. And if you import statistics.jl locally, it will now work. But in order to be very good citizens of the ecosystem, we need to add tests for this package as well. And so Julia has a very standard setup where you have your source folder, you have your test folder, and in the test folder you can click on the run test.jl. This is what all Julia packages have, and you can see that like the first thing when we open up is the middle function being tested. So what we can do is we can add some tests here. So this macro at test lets us add a test. And a test here is just to make sure it's doing what we think we want it to do. And so I'm going to pop back into my notebook here where I have this plot. So we really want statistics.jl to not know about unitful numbers. So we want to design a test that lets us test and make sure that it works for all numbers, but maybe not necessarily add unitful as a dependency. Like we could do the test where, give me the middle of 5 microns and 5 microns. But another way of doing that is if we just test complex numbers, because a complex number is a subtype of number. And if middle works for complex numbers, it should work for any other subtype of number as well. And so what I'm going to do is I'm going to simply add a quick test where we're going to test the middle function. I'm just going to show you all how to use complex numbers in Julia. So if you just do this little im is a syntactic sugar, lets you create a complex number. So if I just call that x, the type of x is complex of float 64. And if you dump that type, it's represented exactly how you would think. On disk, in memory, it's just the real component and an imaginary component. Both are float 64s. That's defined in Julia. It's like 4 lines of code. And it's fast. And so what we can do is we can take that complex number and we can do something like 5.0 plus 2.0 IM, and then add 2.0 plus 3.0 IM. And if we compute the middle, it works, right? Because complex is a subtype of number. And what I can do is just copy paste this as our test. And just throw it in here if I don't spell middle wrong. And then what we have to make sure is to make sure that the type is the correct thing. So I'm going to copy this because I'm lazy. And so does this make sense? The halfway between 5.0 and 2.0 is 3.5. Halfway between 2.0 in the imaginary component and 3.0 is 2.5 in the imaginary component. And then we're also going to quickly just test that the one parameter middle and make sure that that's just returns the same thing. Okay, cool. And so we added those tests, and what we can do is, so this is a little ugly that I have to do this. Normally with Julia packages, there's actually an even nicer thing than using this include, but this will work for now. What we want to make sure is that the test pass that we just added, and it's going to test a bunch of other things that we don't care about for now. And so the middle test pass, all 21 of them pass. So one thing I want to make sure though is that does this test actually capture my new change? Okay, so like if I make a change and I add a test, I want to make sure the old code would have failed. And then, so revise actually makes this really nice. So what we can do is actually, I'm going to quickly stash the changes. So I'm going to stash the changes where now this is back to, like in the source code, we're back to having real numbers. So I deleted the support that we added for any number. So we're back to just real numbers. And so now if I switch back to the testing, the test should fail, right? Because now there's no more support for complex numbers. And what do we see? Beautiful. We get the errors. So it says there are 2 errors. And it says that there's no method matching middle for complex of float 64, which is exactly what we expected. And some cool stuff that happened behind the scenes is revise knew that the stuff changed on disk. It went and switched it out, and we used the old version of the code, and it failed. Perfect. So now what we can do is simply just, I'm not going to show this now, but all we need to do is simply submit, like that pull request is basically done. And so at the end of this talk, I'm actually going to submit this pull request and actually close an issue where I actually think someone also ran into this. Yeah, someone else was using middle and unit full, and they ran into an error, and they were like, "Why is middle restricted to real?" So we just fixed that, and so I'll submit that pull request, and in the next version of Julia, that problem will be gone. And so that we'll have, we added that feature. So I'm going to run really quick to back where I was going, and I've got about 7 more minutes. And so again, I hoped I showed you all a little taste. I hope it wasn't too fast for everyone, but I hope I showed you a taste for how easy it is to, since Julia is written in Julio, and like a lot of the base libraries are also written in Julio, makes it really easy to figure out what's going on, make those changes, understand what's going on. The Julio ecosystem is very robust tooling. There's a lot of robust tooling available, so it's easy to diagnose and figure out what's going on. And so I don't have time to go into this, but there's also a wonderful package called Pkg.Templates.jl. Lets you, like, it's magic. Like, you can go in like a single line of code, generate everything you need to make a Julia package. Like, it adds code coverage, testing, documentation, sets up your licensing. Oh, it even adds like a bot on GitHub to like track your dependencies, and like will like auto make pull requests to you to update your code. Like, it does it for you. If there's a new version of a dependency that comes out, it's great. So you can go from, hey, like, I have a cool function and that I've tested like once or twice, and I want to make a package out of it. Maybe someone else out there could find it useful. You can go from that to releasing the package in an hour. And I did this a couple weeks ago with a very small function. And maybe someone somewhere out there could find it useful. It's been useful for me. And so it's nice to create the packages, even if no one else is going to use it, just because then that code lives in a place, it's tested. You know, when a new version of Julia comes out, it tests it, and it works really nicely. So again, I think the real advantage of Julia comes from the fact that, you know, as a user, like all the, you know, using it day to day, it really prepares you to also develop the language. And it's likely that, you know, as a PhD students or postdocs or scientists in general, like, we're developing new code on a regular basis, and people haven't done the exact same thing that you've done before. And so being able to like, being so highly productive in a language is very useful. And I just love this tweet from another UCSF student who I influenced maybe a little too much, but he like switched to using Julia last year, and he pointed out on Twitter that like, the productivity changes is dramatic. Like, you can go and contribute to all these packages, and we both used Python before, and we rarely contributed just because of the difficulty of contributing to a lot of these base libraries because of the complexities I mentioned earlier. So again, now I'm at the end of the talk. I want to plug the university, the UC Irvine Data Science Initiative as well. They do a very thorough, it's a great guide. Again, these slides will be released and you will be able to follow the link. But I think if you just Google Data Science Julia, it's one of the first links. Yeah, and thank you all so much for listening. You can find me on Twitter, email, GitHub, so on. Yeah, and now if anyone has any questions that they didn't get to ask during the talk, I'll be happy to take them. Thank you all.
Thanks, Tomas. Excellent introduction to Julia. I'm sure a lot of people found it very helpful, and I'm sure we'll have some new converts to the
I hope so.
coding ecosystem. We have a couple of questions.
Okay.
We are over time, so I just want to make one announcement before we jump into some questions. The first announcement is that we will make all the stuff available online. I'll send an email to the group who's here with the link to the recording and the website. We also have a poll that we'd like everyone to fill out if you have a chance. It just helps us for acquiring funding in the future. And I can send that over the chat. I'll send this out via email. Those are my two announcements. We do have 2 or 3 questions that, if you have time, Tomas, it'd be great to get answered.
Yeah.
They're all over the chat, so you can kind of follow along. The first one that I noticed, someone asked, when you were looking at the benchmarking, I believe
Yeah.
you had time. It was the question was, if you have like a more sophisticated call with that benchmark, is it going to benchmark every single function call, or is it only going to benchmark like that entire procedure once?
Yeah, that's a good question. So that is the built-in basic timing function that only benchmarks just the overall function call, like the outer function call. It's definitely that's a limitation of that. There is great tooling for benchmarking more complex code where it will tell you per line what is your memory allocations, what is your how much time do you spend on each function, and it will spit out like per line, give you all the benchmark info. So I think so that's actually built-in into the Julia language itself. So maybe the key word to look for is profile. So the profiling your Julia code, I think there's a whole section on the Julia documentation that I highly recommend. There's a way to run Julia with a memory flag so that you can keep track of allocations and so on, and it will do it per line, so you can get all that information.
Awesome. The next question was about massively parallel environments.
Yeah.
Asking if there was a way that you could develop parallel code in Julia.
Yeah. Okay, so I would say that Julia is second to none in this. I think the example that you need to look at is Celeste.jl. So Celeste.jl is this. I can write it in the chat so you can look at what. See if I can actually spell it right. Celeste.jl. I think that's it. Celeste.jl is cool because it's Julia is one of the very few languages that has actually achieved a petaflop club. So it's one of the few languages that can actually do a peta, like what is, floating point operations per second. It can do a peta of them. And it's the way that was achieved is through massively parallel computation on an enormous supercomputer. And there are very few languages that are actually capable of doing that. I think it's less than 5. It's very few. And so it's definitely fantastic for that. I've done some parallel computation with Julia. I think it's the quite robust facilities for that. Again, I think the Julia documentation is quite good for a lot of people do parallel computation in Julia. And it actually, I think in a lot of ways, it's easier to use than Python's because you don't have the global, the GIL, the global interlock. And so they're like lightweight threads and really easy to distribute code across cores, so if you're using like a HPC environment, I think it's great at that sort of stuff. I'm not the best person to ask about that. But the documentation is quite thorough. And I see that they also asked about 3D plotting. Yeah, I guess 3D plotting, I mean, yeah, you can use Matplotlib, which they already point out isn't that great at 3D plotting. I don't do a lot of 3D plots myself, so I know there's a plotting library that was listed in my slides called Makey.jl that looks like it has great 3D plotting support. The library that I maintain, Gadfly, is quite poor for 3D plots. It's a 2D plotting library. So I'm not sure on that front. So.
Cool. I think that's it.
Okay, cool.
Yeah, thanks so much again for joining us.
Yeah, thank you all.
And I'll let you, if you have anything else you want to say.
No, that's all. Thank you all for having me. And yeah, my contact info was on the last slide, and we'll send it out. If anyone